Okay, hi everyone. We're very happy today at the Barcelona Economic Society to be hosting Professor Michael Woodford from Columbia University. Professor Woodford received his PhD from the MIT, and he's now a professor at Columbia. He's a titan of modern macroeconomics. He has played a key role in developing neo-Keynesian models and influencing monetary policy. One of his key contributions has been the role of expectations, which has been fundamental for policy in the last decades. His new strand of research is focused on the consequences of imprecise mental representations for decision making, which is obviously very related to these expectations for macroeconomics. He has received numerous awards for his research, the latest of which is the BBVA Foundation Frontiers of Knowledge Award in Economics, Finance, and Management, which he shared with Jordi Galí and Olivier Branchard. Thank you, Professor, for being here with us. We're incredibly grateful for you taking our time to share your insights with us. Please, the floor is yours.
Okay, well, thank you, Carlos. It's great to have the opportunity to talk to you. I'm very sorry I can't do it there. Barcelona is one of my favorite cities, and I have lots of friends at Pompeu Fabra, but I couldn't be there this year. The issue that I want to talk about is the advantages for economists of doing laboratory experiments to understand better how to specify more accurate economic models. And the issue that I want to focus on is a very basic question, very fundamental for economics and for macroeconomics in particular, and for financial economics, which is the nature of the expectations about possible future outcomes that people have in mind when making future-oriented decisions. And so this is a very basic question for macroeconomics and for finance in particular, because all of the key decisions that enter into macro models or that relate to modeling financial markets are future-oriented decisions, deciding how much to save or how much to spend, if one is saving, how to allocate those funds between different types of assets. These are decisions that entirely have to do with envisaging being in different possible future situations and finding it valuable to have more funds or not, or more liquid funds or less liquid funds, and so on. And to do this, one has to form a view of the future. One has to recognize that there are many different possible futures. One has to have some sense of the relative likelihood of different possible futures. And furthermore, we want to understand not just do people think there are different possible futures, but how do their thoughts about that change as news occurs? As, for example, when policy announcements are made by central banks. That's an issue that I've worked a lot on. One wants to know how people's beliefs change when new observations occur, because I think that's given that the decisions that are being affected are future-oriented decisions, much of the effect of these announcements is attributable to the way they immediately change the expectations people have about different possible futures. But how are we then going to model the way in which new observations should change the probabilities people assign to possible future events? There's a very orthodox approach in the macroeconomics and financial economics of the last 50 years, which is to assume that people's probability beliefs should represent correct Bayesian inferences from all of the information that's available. And so Bayesian statistics give an answer to the question, if you have certain beliefs based on the evidence you've seen so far, whenever a new observation occurs, how should your probability beliefs change? It would give a precise answer to that. And the rational expectations modeling approach assumes that everyone in the economy's beliefs are evolving in that way. So the question I want to ask is how realistic this model of precisely correct Bayesian inference from new evidence is as an assumption about people in general, which certainly in the case of a macroeconomic model, one wants to know not just what are the beliefs of the most sophisticated people, but say what's the level of spending and saving in the economy as a whole, which is going to depend on what are realistic assumptions about the beliefs and hence the decisions of typical people. So this issue of accuracy of people's judgments about probability, it's been studied experimentally for some decades, and it's long been recognized that people make mistakes when asked to make estimates of probabilities, but not just that they make mistakes, that there are in fact systematic biases, a tendency to misestimate in a particular direction in particular situations, and that these systematic biases seem to be common to many people. Actually, this observation goes back well before the creation of what's known as behavioral economics. It goes back before the development even of the field of experimental psychology. If you go back to the writing of Pierre-Simon Laplace, who was arguably the most important figure in the development of the theory of probabilistic inference, what we call Bayesian statistics. It's for some reason, the Reverend Bayes has gotten his name attached to this field of study, but probably the most crucial person for developing this theory was Laplace. And in his treatise on the subject, his philosophical essay on probabilities 200 years ago, he devotes a whole chapter, at least by the fifth edition of the book, he was devoting a full chapter to what he called illusions in the estimation of probabilities. And so these were systematic mistakes. And he doesn't just discuss the fact that there are particular problems in which it was well known that people were commonly mistaken, but interestingly, for my purposes, he proposes that these mistakes should be understood as what he calls cognitive illusions. And he proposes that these can be understood by analogy to visual illusions that were well known. He says the mind, like the sense of sight, has its illusions. And so what is interesting about this for me is that it suggests to me the possibility of studying people's errors and how there may be systematic patterns in them, but not trying to understand the systematic patterns in terms of mistaken rules, in terms of asking, do people try to apply particular rules to calculate probabilities, but they misunderstand what the rules are. They're consciously following a rule and it happens to be a wrong one. But rather to try to understand the systematic patterns in these errors in the way that it's been common over the past century, at least, to study perceptual processes like vision and the well-known systematic errors that can occur in visual judgments. And so that means that the approach that I'm interested in following is trying to understand the computations that the brain is carrying out relatively automatically, on the whole below the level of consciousness, but producing a sense for a person of how things appear to them without them knowing consciously what rules they've applied to produce this judgment about how the world appears. These processes, I call them computations, and that means as a modeler, I'm going to be interested in modeling the processes by equations, but they're going to be imprecise processes. And so that means the equations that describe them, I think, are going to inevitably involve randomness. And so the equations are going to be describing the randomness in the cognitive processes, as well as what judgments are reached on average. I would further suggest that the approach that I'm interested in taking is to try to understand why these imprecise computations might be of the kind that they seem to be by trying to understand them as a relatively efficient solution to the problem of producing a view of the world that's going to be as accurate as possible on average, but while economizing on the computational resources required to produce one's view of the world. And so there will be mistakes, frequent mistakes. But the view that I'm interested in pursuing is that these mistakes can be understood as a necessary consequence of not using too many computational resources in the way we approach the world, and that it will be interesting to try to understand the patterns in the mistakes by hypothesizing a process that's relatively efficient in what it's doing with the limited computational resources. So this work that I'm going to be talking about today tries to understand people's intuitive sense of how likely a particular outcome, one outcome or another are, given the evidence that they've been exposed to, but from this point of view of seeing them as people whose brains are organized in a way that works reasonably well on average while economizing to a very significant extent on the computational resources that are being deployed. So first of all, what do we know about how accurate people are at judging probabilities? If we ask, do they understand the rules of probabilities? Do they understand Bayes' rule? Can they do calculations that are posed to them as a question that Bayes' rule would give an answer to if you correctly apply the formula? It's well known that most people aren't good at answering questions of that kind. But there is an important literature that has argued that despite that, people are actually quite good at judging how frequently an event occurs, and hence having a fairly accurate judgment of the probability that an event will occur as opposed to not occurring from having seen a bunch of instances on which the event either occurred or not. And this is consistent with what I said before, that I think we want to understand how these judgments are formed by viewing it as largely something that occurs through processes that are not at the level of consciousness and are not dependent on people's knowing the correct rules to consciously follow in judging probabilities. And so this literature that I'm referring to has argued that people may not be good at answering questions about statistical inference that would require them to be consciously aware of the rules by which you would calculate conditional probabilities. They might nonetheless be able to intuitively form relatively accurate judgments of how frequently something happens. There's a famous paper by Peterson and Beach from back in 1967 that argued on the basis of experimental evidence that people are in fact surprisingly good intuitive statisticians. And if that's true, you might think that that's the thing that's actually most relevant for economic and financial modeling, that what would matter for the accuracy of models that assume people have correct probability beliefs would be whether intuitively they have judgments about probabilities, about how often things occur or don't occur, that are relatively accurate, even if they don't know how to justify those probability beliefs by explaining the calculation that would lead to it. So how did people conclude this? The kind of work that Peterson and Beach were referring to and that later papers have continued to pursue typically has used an experimental paradigm in which an experimental subject has to judge the probability of a binary event. It either happens or it doesn't on a bunch of occasions. And there's an underlying probability on each occasion that it either happens or not. That's an independent draw from this binary random variable, binary valued random variable. But in this experimental paradigm, the underlying probability is changing from time to time. And the subject also has to infer whether the probability has changed or not. And so what's happening is that the subject observes a series of binary events, yes, no, no, yes, yes, and so on. And they have to guess at each point in time what the current probability of yes as opposed to no is, which would include inferring whether this probability may have changed or not. So what the literature has often found is what people do is not they don't all do at least the same function of the series of binary events that they've observed. There appears to be a good deal of random variation in subjects' responses to a given stream of evidence. But what Peterson and Beach and other people in this literature, like Gallistel and co-authors, is a more recent paper, they argue that the mean response that subjects give to particular evidence tracks what the correct Bayesian estimate would be actually quite closely. And as an illustration of that, I want to present some evidence from an experiment that I did at Columbia. This was with Mel Kaw and Luminita Stevens, published in the Journal of Monetary Economics in 2017. So our experiment is the kind that I described. There's a binary event. In each session, there are 1,000 draws of the binary event, as shown here on the slide. There's an underlying probability of the binary event occurring as opposed to not occurring. That's varying over time, shown by the black line. So the black line labeled P sub t is this underlying probability that the event occurs. And you see the black line starts out close to 0.7, a little under 0.7, and it stays there for about the first 90 draws of the event, and then it changes. It drops down abruptly from being close to 0.7 to down a little less than 0.2, and then for more than 100 draws, it stays at that lower level, then it jumps up again, and so on. The subjects aren't told this. They aren't told what the underlying probability is, or even when it's changed. They have to produce their estimate after each draw of what they think the probability is. What would the ideal Bayesian decision maker do? The ideal Bayesian decision maker couldn't track the black line perfectly because they only observe the event happens or it doesn't happen, and they can't tell for sure what the underlying probability is from that. But there is an ideal Bayesian estimate, and if you calculate it, it would be this dashed blue line that you see tracking to some extent the black line, although not perfectly. There's a lot of high frequency variation in the dashed blue line, and that's because every time another event occurs or doesn't occur, the Bayesian posterior should adjust a little bit, and so the mean of the posterior, which is the optimal estimate given the way we're incentivizing the subjects in the experiment, would change a little bit. So the ideal estimate should be constantly changing, and it won't perfectly track the true underlying probability, but you see that it tracks it to some extent. What do the subjects do? They don't do that ideal Bayesian estimate. This is one particular subject's data plotted here. Subject 11 is the magenta line, is how that subject's estimate that they're allowed to freely adjust at any point in time is changing over the course of the session. And so they start out guessing 0 for some reason and keep their estimate at 0 for the first several draws. Then they abruptly jump it up. Once they've seen a few draws, they do jump the estimate up to more than 0.6, so not quite as high as what the true underlying probability is, but actually fairly close to it. After a few more ring draws, they adjusted up a little further. They were, in fact, underestimating a little bit. Now they overshoot a little bit, but you see their sense of what's going on isn't so bad. They keep their estimate up above 0.7 for many dozens of draws. When the true underlying probability drops, they don't immediately drop their estimate. But after a dozen or two draws after that regime change, they do abruptly drop their estimate back down to on the order of 0.2 and so on. Okay, so that's what the data are like in the experiment. If we take the data from the experiment and bin all the subjects' responses and all the trials, binning them according to what the P star, the ideal Bayesian estimate was on each trial, that's what's on the horizontal axis here. And in each of these bins, we're averaging the subjective forecasts supplied by the subjects, that's on the vertical axis. What you see is the average subject's forecast indicated by the x's is pretty close to the diagonal, and the confidence interval around it, in fact, includes the diagonal for all the bins. So that's the kind of evidence that Peterson and Beach are quoting to say that people seem to be intuitive statisticians doing pretty well at that kind of task. Here is the raw data, again, grouped that way, but all of the subjects' forecasts when they move their slider that gives their forecast, what they move it to as a function of what the currently correct ideal Bayesian estimate would be. And okay, so they're not nailing it on each individual occasion, but if you ask at each point on the horizontal axis what the average of the points on the vertical axis is, you can kind of see by eye they would average pretty much to noise around the diagonal. Okay, so in more recent work with Arthur Pratt Caraban, who was a postdoc at Columbia, he's now currently at Harvard. We wanted to re-examine this question, looking at this issue more precisely, and we re-examined it in a simpler experimental setting. It's again this series of binary events occurring, but the underlying probability, instead of changing at random points in time, in that previous experiment, there was a probability 0.005 of the underlying probability changing after each draw. In our new experiment, the urn stays the same for 5 draws, and after every 5 draws, it always changes. And it's an independent draw from the uniform distribution of possible probabilities. We tell the subjects this, in particular, we tell them when the urn changes. So they always know when we're starting a new urn and we draw some rings. They're red or green rings that are being drawn from the urn. We tell them it's a new urn. Okay, what do you think is going to be the probability of drawing? We draw a ring. What do you think is the probability of drawing a red ring for the next draw? And they supply a new estimate after each of the 5 draws, and then we tell them it's a new urn now. In this case, where the subjects know where the change points occur, and there are never more than 5 draws from a given urn, the ideal Bayesian calculations are a lot simpler. I can give you a simple formula for it. It would be something people could in principle do in their head if they in fact understood the theory well. Another advantage of this setup for us is that any given informational state, if we ask what's the information the subject has to calculate their estimate of the probabilities, the informational state that's relevant at any point in time will just be the draws that have occurred from the current urn, because they know that each urn is supposed to be independent of the properties of all the past urns. So a given informational state, like the state when we've drawn exactly 3 rings since the urn last changed, and those rings are red and then green, that informational state is going to occur many times over the course of a session for an individual subject, because we only ever draw 5 draws from one urn. So we draw new urns many times. There'll be many times in which we will get to observe what happens after the first 3 draws from a new urn. There are only 8 things that can happen on the first 3 draws from a new urn. So about 1/8 of the times, red, red, green will be the thing that's occurring. And so we'll observe many times what does the subject do when you tell them it's a new urn, and then we draw a red and then a green, and they're making an estimate after that. So we can learn about the distribution, the subject's distribution of responses to each of these informational states, because we observe the same subject responding many times to exactly the same informational state, and they should know that that is what constitutes the informational state. And we can look at this distribution at the subject level. What do we find? So we find systematic departures from correct Bayesian decision making, and not just that the subject doesn't give exactly the correct Bayesian estimate on each trial, but that on average, they're not giving the correct Bayesian estimate. So unlike this claim that, well, at least on average, people basically nail these frequencies, that's not what we're finding when we look carefully at our data. But we also don't find that our subjects exhibit systematic conservatism. There is a literature on how well people do Bayesian inference that has argued that a general finding is conservative bias in updating of probability estimates. And the claim of conservative bias is that people under adjust their estimates to new evidence. And so cumulative evidence that should lead them to lean more in one direction or another, they stay closer to thinking, say, it's a 50-50 probability of two urns being the one that you're drawing from, rather than allowing their probability beliefs to adjust as much in response to the evidence as they should. We don't find systematic conservatism in our experimental results. We don't find systematic overreaction to the evidence either. Instead, we find a very systematic pattern, but of a more complex kind. We find a conservative bias in cases where the subject has observed only a small amount of evidence about a given urn, but when they observe further evidence, the bias switches to overreaction to the evidence after they have had enough evidence about what a given urn is like. Both of those biases are quite pervasive in our data. They're pretty consistent across the different subjects. They're obscured if you were to look for a static relationship between the optimal Bayesian estimate and subjects' responses. And of course, that was the characteristic thing that this earlier literature that Peterson and Beach were writing about typically does. It takes different trials. It asks what would be the optimal estimate on that trial, bins the trials according to that, and doesn't find too much systematic bias. We wouldn't find it in our data either if that was the way we looked for the bias. When we instead condition on more features of the situation, we do find very systematic biases. As a preview of where this is going, I'm also going to suggest to you that we can understand the patterns of bias as a consequence of subjects basing their responses on relatively little information about the evidence that's been presented to them. So rather than optimally using all of the information that's available, we're going to see that their cognitive process can be explained under the hypothesis that it's not too sensitive to the exact information that's been presented to them. And I'm going to suggest to you that we can understand the nature of what's going on by a hypothesis that their cognitive process is one that's economizing on the degree of attention that they have to pay to the information that they've been shown in the experiment in making their response. So I want to talk first about this claim that there are systematic biases. So to talk about the biases, I have to tell you what the ideal Bayesian decision maker would do. And it's pretty simple in this experiment. So the experimental subject should know whenever we say we're drawing now from a new urn, we tell them the probability is independent of anything that's happened before. And each time we draw a new urn, it's equally likely to be any probability between 0 and 1, the probability of drawing red rings from this urn. So the prior distribution should be a uniform distribution between 0 and 1. And we can say after you draw a certain number of red rings and green rings, what should be your posterior, if those are independent draws with red rings occurring with the unknown probability p. And the answer is the posterior distribution should be a beta distribution. It has two parameters, nr plus 1 and ng plus 1. We don't have to talk about what the beta distribution is like here. It's a two-parameter family of distributions. The important thing about telling you that that beta distribution is the posterior is that it implies that two numbers should be sufficient statistics for the information that's available, that's relevant to the subject and what they've seen at any point in time. The total number of red rings and the total number of green rings drawn from this urn are sufficient statistics for the information about the underlying probability, because those two numbers completely specify that beta distribution that I described to you. I can furthermore tell you what the posterior mean is, which is going to be the optimal response of the subject given the incentive scheme that we give them. It would be the mean of that beta distribution, which is given by this formula on the slide. So the optimal response, P star, would be the number of red rings that have been drawn plus 1 divided by the total number of rings. And here is the sum of the red rings and the green rings plus 2. Okay, so for a given number of rings, it's a linearly increasing function of the number of red rings, as you might expect. For a given number of red rings that have been drawn, P star, the probability of drawing a red ring that you should estimate, is going to be lower the larger the total number of draws that have occurred. Okay, it's not going to surprise you that I say our subjects don't give exactly that response on every trial. But what about the hypothesis that their estimates are on average equal to that correct Bayesian estimate? So we can again do the thing that I did with the data from the experiment with Call and Stevens, bin the trials according to what the P star should be on a given trial. For each value of P star, see whether the subjective estimates are equal to P star on average or not. And so this is the figure we get when we do that. In this experiment, the values of P star that occur are only certain rational numbers, because I told you P star is always the number of red rings plus 1 over the total number of rings plus 2. So it's always a relatively simple rational fraction. Only a finite number of values of P star ever occur in the experiment. So I can calculate this distribution of responses for each of those values of P star. The average is given on the vertical axis. And you see the circles are what those average subjective responses are. You see they are hanging fairly close to the diagonal, not right on the diagonal, but you might say that's looking pretty good for the hypothesis that there aren't very systematic biases in people's responses on average. Okay, so the mean response of the subjects, P hat, it's never dramatically different from P star at any point on that interval between 0 and 1. Sometimes it's above, but sometimes it's below. And both when the correct estimate, the ideal estimate, is less than a half, or when the correct estimate is more than a half, you're seeing the average subject response being both above and below the average response. So if there was conservative bias, you would expect to see that when the right answer is less than a half, people would be systematically overestimating it. They would be keeping their estimates closer to a half than the evidence would warrant, and systematically underestimating when the correct estimate is bigger than a half. We're not seeing that here. We're seeing it's sometimes a little above, but sometimes a little below, both when the correct estimate is less than a half and when the correct estimate is more than a half. Okay, so that might all seem very consistent with the hypothesis that subjects' estimates are pretty much the correct Bayesian estimate plus random noise that has mean 0 and is unpredictable. But in fact, we can statistically reject that hypothesis. We can reject it not just on average, but for most of the subjects at the individual level with quite a high degree of significance, and not just overall, but for these individual bins. For all of the bins except the middle of the figure, so if the correct Bayesian estimate is far enough from 1/2, if it's either 1/3 or less, or if it's 2/3 or more, all of those bins, we find that we can reject the null hypothesis that on average the subject's estimate is the correct Bayesian estimate at the 1% level or even less for the great majority of the subjects. And furthermore, the subjects for whom we can reject the hypothesis, we're rejecting it in the same direction for all of them. So when I go back to the figure, what's going on in the figure? There are those dots showing you the average subjective estimate. But those dots, you'll notice, are little pie charts. And what the pie charts are telling you is the fraction of the circle that is filled in as blue is the fraction of the subjects for whom we're able to reject that null hypothesis at the level, 1% level, or even more significant than that. And so you see a lot of those things, 3/4 or more of the pie is being filled in as blue. So a very substantial majority of the subjects are rejecting in the same direction the null hypothesis, even though in some cases that means they're all significantly higher than the estimate should be, in other cases, significantly lower than the estimate should be. But that pattern is quite consistent across the different subjects. Okay, so something is going on that's not captured by that hypothesis, that the so-called wisdom of the crowds hypothesis, it's sometimes called, that if you just average people's average estimates across trials, you get basically the right estimate. Something even more dramatic, we can reject the hypothesis that a subject's distribution of responses are just a function of what the correct posterior would be, what the correct posterior mean would be, maybe in a distorted way. So people who are familiar with prospect theory might be expecting that there'll be systematic distortions in how people estimate probabilities of events, that's some nonlinear function of the correct probability. And that's not enough to describe what's going on here. First of all, that graph I showed you didn't look like the graph that Kahneman and Tversky say that the probability weighting function of prospect theory should be like. It's some much more complicated thing. But in fact, we can reject the prediction that the subject's average response is the same whenever the correct posterior mean is the same. Because we have cases here where the correct P star is exactly the same, although the evidence presented is different. So in the case that the subject has drawn 3 rings, but only one of them has been read, my formula says P star should be 1 plus 1 over 3 plus 1. So it should be 1/2. And let's see, have I done that correctly? No, it's if they've seen none. If they've seen no red rings out of 3, then P star should be 1. Sorry, no. If they've seen no red rings and we've drawn 2, P star should be 1 out of 3 because it's 0 plus 1 over 2 plus 1 over 1 plus 2. So they've drawn 1 ring and 0 of them were red. Sorry. The same thing, though, is true if we've drawn 4 rings and 1 of them is red. Then my formula says it's 1 plus 1 over 4 plus 2, 2 over 6. That's also 1/3. So P star is the same in those 2 cases. We can reject, though, at the 1% level or better for most of the subjects, the hypothesis that their responses are on average the same in those cases. And so that's also indicating when we look at the fine structure of the data, there are very systematic patterns that are not at all like this hypothesis that they're doing something that is just the correct Bayesian estimate plus noise, or even some function of the correct Bayesian estimate plus noise. As I mentioned, the systematic pattern that we find strong evidence for is that there is, in fact, sometimes clear conservative bias and stronger conservative bias when the amount of evidence that the subject has seen is smaller. So, for example, that explains the difference between the 2 cases I was just talking about. In the case when 1 ring has been drawn and 0 of them are red, as opposed to the case when 4 rings have been drawn and 1 of them is red, in both of those cases, the mean of the posterior should be that P star should be 1/3 after seeing that evidence, but there's much less evidence in the first case than in the second case, and we observe that subjects' estimates stay closer to 1/2, are biased in the conservative way more in that first case than in the second case, and that's why there's a statistically significant difference in average estimates in those cases. And in fact, we see this stronger conservative bias when the evidence has been less, very systematically. If we condition on the number of rings that have been drawn and now do this mapping between the objective, the correct Bayesian estimate and subject's average estimate separately for each value of n, we find a nice increasing function, but it's not on the diagonal. And it's different for different values of n. It increases more steeply the larger the n is. So that's what that figure would look like. So now we have the n equals 1 case is one graph, the lightest yellow, then the n equals 2 case, the n equals 3 case, we're doing separate graphs. Again, the optimal P star is the horizontal axis, the subject's average estimate on the vertical axis. And we see it's not the same relationship independent of what the number of rings drawn are. And we see that when n is small, we have conservatism. We have an increasing relationship, but with a slope definitely less than 1. Whereas when n becomes larger, when n is 4 or bigger, in the middle of the graph, the slope is now greater than 1. And when n is 5, we have overreaction globally. You're below the diagonal for everything when p star is less than a half, and be above the diagonal whenever p star is greater than 1/2. Okay, so that's what in fact is the simplest description of the systematic biases that we find here. We can see that figure even more clearly if I plot the bias. So now the vertical axis is the difference between the subject's average estimate and what the correct Bayesian estimate would be. So the Bayesian should be a flat line at 0 on the vertical axis. And we're seeing how these average subject estimates differ from 0. Downward sloping is conservatism, upward sloping is overreaction to the evidence, and we're seeing how that slope systematically changes as we increase the number of rings that the subject has seen. Okay, so how can we understand? There's a highly consistent pattern of bias here. How can we understand what's going on? So Arthur and I argue that what we see here is evidence that subjects' estimates are based on a cognitive state that provides much less information about the evidence than what would be used in the correct Bayesian estimate. And this available information seems to be inadequate in 2 respects. So first, we argue that the process that accounts for people's data is one in which the cognitive state seems to provide only a noisy record of the evidence that the subject has seen. And so the noise in the cognitive state propagates as additional evidence is observed. So the extent to which people are off from what they should have recorded that they've seen involves errors, and those errors then propagate as they observe additional evidence. Secondly, this cognitive state seems to vary only along one dimension, whereas, as I pointed out, you would need a 2-dimensional summary of the evidence for correct Bayesian inference. And so that's another sense in which it seems the cognitive state is providing much less precise description of the evidence than what would be involved in exact Bayesian inference. So I don't think I have time to tell you too much about what the evidence is like on these 2 things. We can look at serial correlation in the departures of people's estimates from the correct Bayesian estimate because we observe them facing the same informational state repeatedly. So we can ask for each subject how their estimate on a given trial differs from their average estimate when they're in that informational state. And we can then look furthermore at the serial correlation patterns in those departures from their average response to a given informational state. And you see here there is positive serial correlation. This is just looking at the correlation between that departure from average response on one trial and the next trial. The correlation is above 0.6. It's statistically significant at more than the 1% level. We can furthermore look at this for different lag lengths and conditioning on what number of rings have been drawn so far. We get patterns of positive serial correlation of different sizes. We want our model of the cognitive process to explain this. The fact that the serial correlation is positive and statistically significant is indicating not just randomness in the cognitive state, because the subject says different things on different occasions when they've seen the same evidence, but that this randomness propagates from one trial to successive trials in the draws from that same urn. Secondly, we provide evidence that the dimension of the state that the cognitive state is moving on seems to be one-dimensional. I won't talk here about how we plot the data to show this, but we're able to plot our data in such a way that we should see the points falling on a two-dimensional space. If we had an ideal Bayesian decision maker like what's seen at the right, and instead the points are sort of squashed on top of each other, so they're pretty much on a line rather than filling this two-dimensional region. And we look at that from several different directions and verify that it looks like the data are lining up as if the cognitive space that the subject's mental state is moving in is one-dimensional rather than two-dimensional. So we propose then a relatively parsimonious model of the cognitive process that we call a noisy counting model that has these properties. We show that simulations of this cognitive process model produce data that look a lot like our subject's data. So the idea of the noisy counting model is it's assuming there's a cognitive state that's on a line. Each time another red ring is drawn, you jump your position on the line in one direction. If a green ring is instead drawn, you jump your position on the line in the other direction. If you jumped a certain amount precisely each time a red or a green ring was drawn, and it was the same size of jump, but in opposite directions in the two cases, then this would be a precise count of the net excess of red rings over green rings. The noisy counting model is noisy because what it assumes is that the size of the jump is an independent draw from a non-degenerate probability distribution. It's a log normal distribution of the jump sizes. And so the cognitive state then involves noise that then propagates as additional evidence is collected. Okay, and this is comparing simulations of that noisy counting model to our subject's data. These are three examples of plots of the subject's data. In the upper half of the figure, the corresponding plots of the simulated data from the noisy counting model. At the bottom, over at the right, you see that when we plot the data in this particular way to see what dimension of space the cognitive state is moving in, it looks a lot like moving on a line in the noisy counting model. You see at the bottom, similar to the data from the subjects. The degree of autocorrelation produced as a function of lag length and as a function of number of rings that have been drawn is similar to what we get with the subjects at the top. We get a similar figure from simulation of our model. That autocorrelation is coming from the feature of the noisy counting model that I mentioned, that the jump sizes are random, but then the position that you've jumped to is the position that the next jump moves from, and so that introduces this positive serial correlation in the randomness in subjects' probability estimates. And finally, you see that sort of spider web pattern over at the left, the nature of the systematic bias moving from systematic conservatism when only one or two or three rings have been drawn to overreaction to the evidence when four or five rings have been drawn. That's also coming from the noisy counting model. And the reason the noisy counting model produces this is because subjects are adjusting in the right direction, their estimate when they observe a red ring or a green ring. Observing a red ring makes them increase their estimated probability of drawing red rings. Observing a green ring makes them reduce it. But the ideal Bayesian estimate would not move the estimate by the same amount independent of how many rings have already been drawn. So if you go back to that formula, it was a linear function of the number of red rings, but it had the total number of rings in the denominator. And so the formula said when you draw on the first trial, you haven't drawn any other rings yet, you should adjust your estimate by a relatively large amount, depending whether it's a red ring or a green ring. After you've observed several rings, the next red ring, you should still adjust your probability estimate, but by a smaller amount. And so you should adjust by progressively smaller amounts the more evidence you have. The noisy counting model is not doing that. It's therefore producing underreaction to evidence on the early draws from the urn, but eventually overreaction to the cumulative evidence once a sufficient number of rings have been drawn. Okay, so that's an algorithm describing a mental process. It seems to match salient features of what people are doing. Why would people's behavior, though, be described by an algorithm of that kind? Our interpretation is that this is a cognitive process that economizes on the attention that has to be paid to the specific details of each of the individual situations in which the subject has to be giving a response, so they can give a response without the cognitive mechanism that produces the response having to have paid precise attention to the series of draws that have been reported so far, taking into account this additional consideration that it's going to be economizing on the precision of the attention that's paid to the details of the situation. This process might be fairly well adapted to the decision task. This is in line with what are called theories of rational inattention, and our approach belongs to that general family. In what sense is the process that I proposed economizing on attention? Well, you'll notice it doesn't use any information about the prior history of draws apart from what the subject's own most recent estimate is. They Their next estimate will depend on what the most recent estimate is because they'll move relative to that, but that's information that they still have because they've moved a slider. The position of their slider is telling them what their most recent estimate is. They're not having to keep in their mind other information about the series of ring draws that led them to move the slider to that position. That fact means they can't condition the amount that they're going to adjust to the next ring draw on their degree of certainty about the current estimate. And so that's what's going to lead to this systematic pattern of overreaction when there's only been underreaction when there's been only a little bit of evidence, but overreaction once they've received more evidence. They're not keeping track of how much evidence has come. That's going to economizing on that degree of detail in their information that they're using about the situation that they're in is going to result in the systematic pattern of bias. In fact, the process economizes on attention to an even greater extent because it assumes that the size of the change in position that the subject executes isn't even being conditioned on what the current estimate was, whether it was a high or low current estimate of the probability of ring draws. It's only conditional on whether you've drawn a red ring or a green ring. So it's not being conditioned on very much. And that makes it a simple strategy to execute in terms of the informational requirements of executing the strategy. Furthermore, we're modeling the subjects as exerting only imperfect control over the size of the adjustment that they make. And so that allows them to economize on attention to the precise slider position that they move to. So they move to somewhat the right amount when a red or green ring is drawn, and it's a different movement depending whether it's a red or green ring, but they're not precisely calibrating the amount that they move. In what sense would it make sense to say that their behavior may be nonetheless well adapted to the task environment? Well, those informational economy concerns that I was describing would tell you that it should be saving on information costs to do something like a noisy counting model, but it doesn't tell you what the average size of slider adjustment should be when a new red ring as opposed to a new green ring is drawn. You might have an average adjustment of 0.1 on average, or you might have an average adjustment of 0.05 on average, and the degree to which those versions of the noisy counting model would economize on information about what's going on in a particular trial would be the same. In fact, we can ask what determines what the average size of adjustment is, and the answer is it's close to optimal for our task. So we can estimate a parameter mu, which is determining the average. It's a parameter of this log normal distribution of adjustments. It's determining the average size of the adjustment when a new red or green ring is drawn. The size of that mu that best fits our subject's behavior is close to the one that would be optimal in the sense of minimizing the mean squared error of the subject's estimates. They would make a higher squared error on average if they had either smaller adjustments on average or larger adjustments on average than the ones that they're doing. One way that we can see that there's something to this hypothesis that they're to some extent able to optimally adjust the size of their adjustments to the statistics of the environment that they're in is by observing that what this optimal mu is depends on the fact that the experiment is not just this particular kind of binary event that you're having to forecast the probability of, but that we draw exactly 5 rings before each of the regime changes. So that means that the rule that you're applying will only be used on occasions when you've drawn 1 ring or when you've drawn 2 rings or 3 rings or 4 rings or 5 rings, and it'll be used equally often in those 5 situations, but not in situations other than those. We in fact find that if we vary that aspect of the experiment, the subject's average jump size in the noisy counting model is a somewhat different. So in our main experiment, exactly 5 rings are drawn before each of the regime changes. We also have a variant design for the experiment where there's a constant probability of a regime change after each ring draw, like in that other experiment that I had described to you at the beginning. But this constant probability of regime change is chosen so that the mean number of rings per regime is again 5. And we're again going to tell subjects whenever a new urn is drawn. Okay, so how does subjects' behavior change when we do the variant as opposed to the main experiment? What's being plotted here first, these curves are what simulations indicate mean squared error would be under the noisy counting model for different values of the parameter mu. So you get a U-shaped curve. So you want a particular intermediate value of mu to have mean squared error be as small as it should be. For the main experiment, that curve reaches its minimum around 0.09, and our median subject's value for mu is around 0.08 instead, but they vary over a range. You see there the interquartile range is sort of between 0.07 and 0.09. So they're not adjusting at too much smaller a rate than what the optimal adjustment size would be in that environment. Even more interestingly, if we do the same kind of simulation for the variant experiment with the geometric distribution of regime lengths, now the mean squared error as a function of mu in this new environment would be the orange curve instead of the blue curve. It would be optimal to adjust a little less to each ring draw in this environment, because now you have an environment where sometimes as many as 10 rings might be drawn from a given urn, although sometimes only 1 or 2 rings are drawn from a given urn. In that environment, it's optimal to adjust by less in response to each red and green ring that's drawn, and the subjects are indeed adjusting by less. So the box plot in orange down at the bottom of the figure is showing you the distribution of estimated values of the parameter mu for our different subjects, and that distribution is definitely smaller and largely non-overlapping with the distribution of mu's estimated in the case of our main experiment. So it seems that subjects are doing something similar, again described by a noisy counting model, in the environment where we change the probability distribution of lengths of regimes, but they're not doing exactly the same thing, and their behavior is adjusting in a way that in fact improves their performance in terms of the incentives that we're presenting them. Okay, so to summarize, what we have shown using this laboratory experiment is that people's probability estimates we find are biased, but they're biased in a way that varies with the amount of evidence that's been available to them. Sometimes a clear conservative bias, sometimes a clear overreaction to the evidence bias. We find both underreaction and overreaction occurring, but at different times. Underreaction to the first evidence that the subjects receive about what they understand is a new situation, but at the same time, overreaction to the cumulative evidence that they've obtained after what they understand are repeated observations from the same situation. We furthermore argue that those biases are something that can be understood as a natural response of subjects' decisions being based on relatively minimal information about the situation that they're in on a given trial. They're not responding to much information beyond what the current ring draw is, whether they've just drawn another red or green ring, and they're not paying completely precise attention to that. In particular, they're not very perfectly controlling the response they make even to that information. We summarize the sense in which that's true with our noisy counting model. And my slide has frozen here, but I guess I will sum up by saying the broader picture that comes from this. First of all, we find evidence that even though people are certainly not ideal Bayesians, the idea that their behavior adjusts to the statistics of the environment they're in is something that there is support for. And this adjustment seems to occur even relatively quickly because these people that are adjusting to the distribution of regime lengths associated with the variant experiment as opposed to the main experiment are having to notice that the statistics are different and adjust their behavior to them relatively quickly. This is occurring over the course of a session that is less than an hour. So after some minutes of experience with this new regime, they are adjusting the parameters of the behavior. And so that's the sort of thing that the rational expectations hypothesis was introduced into macroeconomics to deal with, this idea that we shouldn't expect that we can estimate people's behavioral rules based on what people did in past environments and then predict that they'll behave in the same mechanical way in a new environment created by new macroeconomic policies, for example, rather than thinking that we need to think about how it would make sense for them to adjust their behavior to the new environment. We are seeing our subjects' behavior adjust to a new statistical environment and adjust relatively quickly. So it does seem that occurs and that a hypothesis of adaptation in a way that's useful to the subjects, given their incentives, is of value, but assuming exact rational expectations would not give us at all correct conclusions here. We need to have a model of how people try to adjust adaptively to changes in the environment they're in, but it's going to need to be a model that takes into account the fact that people are often economizing to a very significant extent on the extent to which their cognitive process is taking account of the exact details of the situation that they're in. And so that's the issue that I think we as economists need to study much more. In doing it, I think that laboratory experiments of this kind can give us a lot of insight into what the relevant constraints on cognitive processing may be like. Thanks.
Thank you, Professor. We'll open a turn of questions. You can unmute yourselves or ask your question in the chat. I'd like to ask, to warm up the room, I think I wanted to ask you more about how you conducted your experiments. I'm assuming it was in a risk-neutral setting. One thing that I think it's could be interesting to see is that how people behave in risky situations. So, for example, how does this probabilistic thinking may change in a situation of crisis, right? Maybe people don't always behave rationally in times of crisis. So I think it would be, have you thought about that? Is that something you plan to tackle at some point?
Well, I mean, that's exactly the kind of issue that I think we need to undertake this kind of study for. Now, you were suggesting that maybe the thing that you need to think about is how people respond to heightened risk. And you might say, well, this experiment, at least the one I told you, wasn't creating any significant risk. You might expect people to be risk neutral, and that's right. And there's a reason why it's true, which is that the ethical constraints on the kind of
Yeah, of
laboratory
course.
experiments we can conduct on Columbia students is I can't put them into any situation where they are suddenly made to believe that they're at any genuine kind of risk, and so I can't see how would their decision making be affected by that. But something that we can study that I think is relevant to understanding what might be different about crises is something else that's true about crisis situations is that people become aware that the situation is not the one that they're used to. And what we were directing attention to, I mean, this is, it's a very simple, very stylized kind of experiment, but what we were directing attention to with this experiment was a difference in the way the biases in people's guesses about probabilities are related to the evidence that they've seen, how that is different when they believe that they're facing a new situation and the things they've seen before don't tell them anything about the urn that they're currently drawing from, because the experimenters have told them it's a new urn now and it's been drawn independently of what all the past urns were, versus when they're in a situation where they're being told, um, we're drawing more rings. It's the same urn that we've already drawn several rings from, and we guarantee that we have not changed the urn on you. So what you've learned from those first several ring draws is still relevant to what you should expect the next ring draw will be. And we're finding interesting differences in the biases in people's probability estimates depending on that. And I think, again, this is a very simple situation, but I think it's very revealing to look at how the way people try to use that evidence to form estimates of probabilities is different depending on on whether it's a situation where, in fact, they have and should understand that they have little experience with the situation they need to try to forecast now, or it's one that they have a lot of previous experience with, or that at least they think they have reason to think there's a high probability that the situation hasn't changed very much from the one that they've observed a lot in the past. And so if we can understand better that kind of issue, how is behavior different in familiar settings where there's a lot of relevant previous experience, and in settings where decision makers themselves have reason to suspect, at least, that the world is very different right now. And because that's certainly a lot of what's going on with crises. And when you say people are aware of risk, I think a lot of it is that. I mean, it's not so much that they know exactly what the things are that can happen, but they know that they have a much higher variance than they had in the past. It's more that in the past they thought they knew more about how to bound and assign probabilities to the things that can happen, and suddenly they're in an environment where they realize they can't, they don't have as much basis for saying from previous experience that they know what is the range of things that can happen to them. And I think that kind of uncertainty, what's sometimes called Knightian uncertainty, is in fact suddenly very relevant in crisis situations. And that's a little different from the issue of asking how would they believe if the risks are perfectly understood, but you perfectly understand that now you're at risk of a big loss, and before you didn't think that that was one of the possibilities.
Okay, thanks. We have a question from Sumit. I see you have your hand raised. You can ask your
Yeah.
question.
Okay. Can you hear me?
Yes.
Yes.
Okay. Thanks. Thanks a lot, Professor Woodford, for the very insightful and thought-provoking lecture. So I was drawing parallels when you said wisdom of the crowd. First thing came to my mind was prediction markets, and I mean there has been a recent paper, in fact, on prediction markets where they say that it's not really the wisdom of the crowd, but a wisdom of an informed minority. Where they make the decisions and the whole crowd kind of sticks to what the informed minority is looking at. So your experiment, do you draw parallels, on how what your experiment suggests and how the prediction markets really work? Because if, for example, if I take a case of, say, right now what's trending a lot is, when is the Strait of Hormuz going to be opened? And it started off, say, end of May, and then there are contracts for end of June, and further on. So with what you're saying, it seems that as we go forward, and the market should invariably be much more volatile in their predictions of, when uh, I mean the probability basically should be on the higher end of, like, the extreme case rather than the more conservative case, as we go further into, into the year, and we don't see that result happening, right? So I was very keen to understand, can we draw those parallels, and how do you think about what your work does, and how do prediction markets work? Because at the end of the day, they are also binary contracts. So if you can just throw some light on that. Thank you so much.
So, I mean, that's the kind of situation that I would like to be able to understand better. I mean, I have not tried to model specifically prediction markets, and there are clearly other issues going on besides what we're studying in this experiment. I mean, this experiment is an individual decision experiment, and so there are no issues um, of asking what is the effect of many different people with their different beliefs trading together in a single market. Um, and in particular, in understanding the prediction markets, I mean, I think the issue of some people being more informed than other people is also, likely to be important to understand what's going on. And once you introduce the fact that some people can be better informed than others, then you need to ask how even uninformed traders in the market ought to be adjusting their trading given their awareness that other people in the market may well be better informed. And so those are considerations that are just not present at all in the kind of experiment done here. But the sense in which you're right that prediction markets would be an interesting case to study is that they are a case where you have people being allowed to adjust over time the probabilities, the bets they're making, so implicitly the probabilities they're assigning to a binary event as additional information occurs. And because these are bets on an event that is connected to a particular date, it means that you do get to observe both what the probability estimates seem to be of the people bidding in the market early in the process. A new contract has just been proposed, and maybe it's about something there's not too much information about yet. And then over time, you're observing how those estimates are changing with more information. And that is indeed exactly the kind of thing that our experiment is suggesting it should be interesting to look at, and that markets where you can clearly differentiate estimates after more information from estimates that were made earlier when less public information was available. This theory is saying you should see systematic biases that you would expect to be different. But again, the behavior in our experiment can't just be directly put into a model of the prediction market, because it's not introducing how should people's betting be affected by their awareness that some informed people may be trading. Someone who's involved in deciding whether the U.S. should send battleships into the Strait of Hormuz or not, or something, could themselves be betting on this question.
Thank you.
Okay, we have a couple of questions on the chat. Gabrielle says, asks if you could elaborate a bit on the implications of your findings on one, the best way of modeling expectations with rational intention, and two, policy implications in monetary policy or financial economics.
So I'm certainly interested in versions of rational inattention models, and I have tried to show you how this kind of experiment I think provides interesting evidence that something that at least belongs to that broad family is a promising way of trying to model expectation formation. So what that means is, certainly that expectations should not be modeled as just arbitrary parameters, that people have expectations and it's an arbitrary fact about them, like the way they have arbitrary tastes, and it's just a parameter of their decision rule. Unaffected by the information that's been provided to them. I think that one should model people as responding to information and their beliefs evolving as additional information occurs. That's certainly going on in our experiment, even if what people are doing is not at all the exactly optimal estimate. They are clearly adjusting their estimate each time a new piece of information comes. They're adjusting it almost with probability 1 in the right direction. I didn't show you a figure that shows that, but we do study that, and we show that it's virtually perfect. If you ask what's the sign of the change in subjects' estimate of the probability, how that relates to whether the evidence that's just been observed should increase or decrease the probability estimate, they get that almost perfect. So having a model that is modeling beliefs as evolving in response to evidence is clearly needed. At the same time, it has to be something that differs from perfect Bayesian inference. I would say it should differ in the direction of assuming that the record that you're carrying on in your cognitive process, the record of the past that you're carrying on, is something much more compressed as a summary of what you know from what you've seen so far than an exact record or even exact knowledge of what the sufficient statistics for a Bayesian decision maker would be. And the tricky part is deciding, okay, what's the cost function for having a more precise record of what evidence has occurred? And in the rational inattention literature, there have been a variety of proposals for what these cost functions for precision should be, and the details of your model of the cost of precision are going to determine what the detailed implications are. Some people have taken the approach that you should find what you think are beautiful axioms for costs of information and build then a rational inattention theory on that. I tend more to the view that we should try to figure out what's the realistic cost function from looking at experimental evidence of the kind that I've illustrated in this talk, looking in detail at the ways in which people seem to be making use or not making use of different aspects of the information that in principle was presented to them. Again, I didn't have time to go into too much detail into how we try to study from the behavior what we can conclude about the way in which the cognitive state seems to be an imprecise record, but I believe there are ways to try to do that from experimental data, and then one can ask what kind of cost function would correspond to the ways in which people seem to be in fact, economizing on information. And I think that's what will ultimately be the way to build up a better theory. You were asking what are the implications of this for macroeconomics and finance, and broadly, I would say you certainly should not be putting a lot of weight on predictions that assume or they're at least very sensitive to assuming that people's beliefs are precisely correct ones, conditional on all the publicly available information um, at a given point in time. At the same time, uh, assuming people just don't look at information is also going to be wrong. And so, for example, I think these results are consistent with the view that policy announcements matter. I mean, taking the idea that talking to the public about what the logic of policy decisions is doesn't matter because whatever your systematic rule is, people should correctly understand the systematic rule. Well, I don't think that's right. Given that they're economizing on the records, even of what has been publicly observable, that they're using, making things that you want them to be aware of and to condition on more vividly part of their awareness by drawing attention to it through public announcements, I think can matter. So I think that this view that people economize on information is actually something that leads to increased reason to be concerned with communication by policymakers, but at the same time, just assuming that whatever information you think you've provided, they have, of course, absorbed, and they're drawing the inferences that you think are the correct inferences from it, precisely is something that you want to be careful about. You should not be surprised if the response of the public to an announcement is quantitatively less often than what you think the ideal response is. If they understood what you told them and they completely believe what you told them, instead, you should expect that their cognitive process is going to be responding to the information, but responding in an imprecise way.
Okay, thanks. Another
Hey,
question?
I had a
Oh,
I had a question.
sorry, Marty.
Oh,
There's
oh,
one.
there is another.
Yeah, yeah. Sorry. There's just I'm going by order. So we had two questions in the chat, and then you raise your hand. Sorry. So Arnav asks. Oh yeah, sorry. Arnav
All right.
asks to make a question. So you can just unmute yourself.
All right. Thank you so much, Corals. Professor Woodford, I'm actually a high schooler in the US and I'm really interested in macro and finance. And, I really enjoyed your presentation, especially the connection between, intuitive probability judgment and the implication it has for macroeconomics. So in your experiment, people didn't really update like perfect Bayesians. They seemed to use a rough mental count, which made them underreact initially and then overreact later. So could something happen similarly within inflation expectations, where people kind of combine, Fed signals into a rough overall view instead of updating precisely? And if this is true, would it change how economists should model the impact of repeated central bank communication?
I mean, yes, I think it should change it, and that's why I'm interested in studying this as much as I am. And as I said, I mean, speaking very broadly about the kind of implications it would have, I think it's it's going to mean that you should not be surprised if the effects of central bank communication are not perhaps as large or as precise as what you think the effect ought to have been of what you thought you told people, and what they ought to understand the implications of it are, but that I don't think that means that therefore there is no point in central bank communication. I think that both that the evidence suggests that people um, are responding to information, also that the amount that they're keeping in mind a perfect record of the things they ought to have been able to learn from past experience is also perhaps quite limited. And that's a reason to say that saying things again may matter, even if you say, well, you say, I've said it before, and so they should already know it, or they should already have been able to see it from my behavior, so I shouldn't have to talk about it. Actions should have already made it obvious. I would say, no, it doesn't mean that it's irrelevant to say again what you hope that people will be able to see in the pattern. So I think it will change our view uh, of of how you should conduct communication policy. It will not make communication policy irrelevant. You might argue that it makes it more important. On the other hand, I think it also suggests that what you communicate needs to not be too complicated, because what people are likely to respond to, I mean, in general, what they respond to about their environment is a simplified description of the environment relative to all the things that are actually true about the environment. I think that's going to be true of central bank announcements also. They're going to respond to them, but they're going to respond to, if it's a complex signal, then you should expect people to be responding to a simplified description of what was in that complex signal. And that's, in fact, the reason why communication is probably going to be more effective at producing the effects that you want, if, in fact, the signals are themselves relatively simple and relatively clear in their implications.
Thank you so much. Yeah, absolutely.
Fantastic. Thank you. It's your turn now, Marty. Thank you for your patience.
I'm not hearing you. Sorry, you're muted. I think you're muted.
I'm sorry. I know that we are beyond the schedule, so just bear with me for 3 minutes. It's just two questions. The first one is regarding the modeling of the states. I was wondering if it was modeled with a finite state machine, perhaps with Markov chains. And the second question was more irrelevant to historical evolution of information propagation, because in the past everything was spread through newspapers, which meant that reaction to information was simultaneous. So you had a lot of different points of information and people reacted to that. And now everything is atomized, which in the sense that everything comes at different times and people reacted. And then the reaction affects the next reaction with more frequency. So I wanted to ask, for this second question, if your experiment includes some information and insight into this idea, if perhaps precision increases when you have more frequency in the enforcing prediction, right, to that information. Yeah.
So I think the answer is no, that we haven't studied that second question. I mean, I think it's a great question. I mean, again, if you ask, why do I think it's valuable to study the kind of issues we're trying to study? I think the changes in the world that you're referring to are reasons why we would, I think we need, to be able to think about these things more. So one of the reasons to want more of an understanding of the underlying cognitive processes is because behavior is likely to change in the new kind of informational environment we're coming to be in, which, for the reasons you were summarizing, is not the kind of world that I grew up in when I was young. The kind of information that's available in the environment, and it's not just quantity of information, but as you said, the degree to which it's synchronous or asynchronous, and these kinds of things are changing and changing, fairly rapidly. For us to have an idea how to change our models, we have to go beyond just saying, well, we've seen how people seem to react to certain kinds of shocks to the economy in the past, and we'll just assume those same estimated responses in the past should be the same. Quite possibly not. And to have some kind of handle on how changes in the informational environment might change behavior, I think we need more of a structural understanding of what it is that determines the way people respond to information. But I guess I can't satisfy you by saying I have already studied the particular question that you're posing, although I appreciate why it's interesting, and indeed I hope it, I think it's the kind of thing that ought to make people more interested in digging further into the kind of questions that I was talking about in the lecture.
Okay.
Thank you.
Fantastic. So I'll say just a few words because this is the last talk of the year. I just wanted to take a moment to say thanks to you, Professor, for allowing us to close with such an impressive scholar as yourself. And I wanted also to thank the other professors who have given their time to speak about their passion, which has really enriched us and helped us grow as young economists and as a society. Thank you also to the people who've come regularly to our events, which have also helped to keep this society functioning. So thank you, everyone. I hope you have a great day, and we'll see you next academic year. Thank you.
Thanks for having me.